Every good story needs a good illustrations, and illustrating logics is not an exception. In these clumsy drawings, I try to give a reference to Venn diagrams where supposedly circles of equal size are positioned in such a way that all combinations between groups and circle represent the group. So all combinations are visible, and in case of Euler diagrams, there are no strict rules. It's the only rule is probably proportionality of the circle sizes to the group sizes, and then it can be included or not included, intersected, not intersected. It's up to everyone. The history of it is pretty long. It begins with Aristotle. Well, we skip the details, but he didn't draw circles. The first mathematician who used circles to illustrate logics was probably Gottfried Wilhelm Leibniz. But he didn't publish his works, and circles were exactly about illustrating logics. And Leonhard Euler very likely knew about works of Leibniz, and he published more or less the same circles in his letters to the princess. It was a series of educating letters where he had to explain in simple ways some fundamentals of mathematics, and these illustrations were exactly to the point. There was another guy in between, Christian Weisse. In some books he is also cited as inventor of the circles, but it's not really clear, and therefore we mention him, but we don't give much details what he did. Maybe he did not. Then it was, of course, Leonhard Euler. He was a so big figure that he is cited many times in many directions, and his diagram rightfully carry his name and used until now. Then there was a fresh start with a Boolean math, which was actually in the mid 19th century, but he didn't draw circles. After Boole, there was a John Venn, and then he decided to reinvent Euler. He referred to Euler. He said he probably appreciated Euler, but he claimed he improved Euler by fixing the position of the circles in the way we know it now. And the way we know it now is nicely presented in Wikipedia. You see those logical constructions, and in red you see what it means. For instance, intersection between two groups is this area where common elements are coming, and union is everything, and symmetric difference is all but intersections, and so on, so on. In the biology, we actually interested most of the time by intersection, nothing else. Long version of this story can be found in a PDF, Origins of the Venn Diagram by Deborah Bennett, which is published in a book Researching History and Philosophy of Mathematics. She reproduces the drawings of Venn, but also adds this figure, which opened the Pandora box, meaning how many circles you can make, which would obey the rule of Venn diagram. You probably realize that If you have 4 groups, this is not the way you draw Venn. It's more like a German car. Venn also suggested this sort of ovals of ellipses to combine 4 groups. With the 5, it already became obvious is getting more and more complicated. And this is another way of trying the 5th element. Drawing 5 elements Venn diagram is very well possible nowadays. You can see examples on Stack Overflow page, for instance, and many other places. Another example. What is interesting is actually another example from here. It's a 7 elements Venn diagram. And here you see a problem that more elements you add, more congested is the active area where you place your results of intersections of different combinations. I did not check the latest, but a while ago it was these publications with the claim that this is the world record breaking achievement in drawing Venn diagrams with the symmetrical elements. It is 11 set combination. Again, the problem persists that the active area where you place all the results of intersections is now ridiculously small. So it is a very nice as a picture on the wall, but it is completely useless as an illustration for some scientific work. Nowadays there are some web applications where you can draw your Venn diagrams based on your own data. This is example of 3 with the references below. And not for nothing they limit themselves to sizes of 4, 5 or 6 for a practical reason. There is no point of drawing more complex Venn diagrams even if it is theoretically possible.